there. Our lesson today is fuels and energy. The applications of stoichiometry in combustion reactions. So, for fuels and energy, the objectives of this lesson are to, number one, to distinguish combustion reactions from other types of chemical reactions. Number two, write combustion reactions properly. And number three, to demonstrate the ability to solve problems involving the application of stoichiometry in combustion reaction. So what is combustion reaction? This involves the reaction of a material with oxygen to produce oxides of all other elements as products, releasing energy in the form of heat during the process. It is also commonly known as burning. If you would see this equation here, so we have here your fuel plus O2, it's pronounced as oxygen, equal to carbon dioxide or CO2 plus water or H2O. So it would be fuel plus oxygen would produce carbon dioxide and water. So this is the general equation for combustion. For fuels, these are normally made up of elements that readily react with oxygen, such as carbon and hydrogen. So example of these are butane, propane, and liquefied petroleum gas. So we have here an example. So this is your propane plus oxygen would form 3 carbon dioxide plus 4 water. So you have here your butane plus 5 moles of oxygen forming 3 moles of carbon dioxide and 4 moles of water. So you also have here your butane. You have, for every 2 moles of butane, you can produce plus 13 moles of oxygen. You will produce 8 mole of carbon dioxide plus 10 moles of water. So these are examples of combustion reactions. If you notice this, they have coefficients, and this would confer the law of conservation of mass, which states that matter can neither be created nor destroyed. So here you have there the reactants. In this table you have the reactants, and then you have the elements, and then you have the products, and then you have again on the other side you would see reactant, elements, and products. Okay, let's see first for the butane. Let's see first for the propane. So we have here 1 times 3 is equal to 3, and 5 times 2 equals to 10. 1 times 8 is equal to 8. So this corresponds for carbon. So carbon there, you only have 1 carbon from this reaction above. So you have C3H8, and then you have 5 oxygen there. So you would see there 1 times 3 coming from this here, the C3, and then we have oxygen is next. So oxygen, we have here 5 times 2 because we have there 5 O2, right? And then we have hydrogen as 1 times 8 because of the 8, because it's C3H8, so it's 1 times 8. So for the products, you would see there you have your carbon dioxide and water. So you have 3 CO2 plus 4 H2O. So if you would see there the CO2, the other side, the carbon is 3 times 1 equals to 3, and your oxygen your oxygen is 3 times 2 there from 3 CO2, so 3 times 2 plus 4 times 1 from the water. And then for hydrogen, you have 4 times 2, 4 times 2 there, up. So both carbon is 3, oxygen both are 10, and hydrogen both are 8. So these are a balanced reaction. So at the same time with our butane, we have there 2 times 4 for carbon will equal to 8. And the other side, it is 8 times 1 equals to 8. So from this equation, you would see here, you have 2, see there, 2 times 4 for your carbon here, and you have here on this side is 8 CO from the CO2, and you have 13 times 2 for oxygen. This one is 13, so times 2, and then on the other side is 8 times 2 from the carbon dioxide plus 10 times 1 from the water. You add this, the sum of this is 26, so it's balanced. Then you have 2 times 10 for hydrogen, the 2 times 10 there. And then on the other side, you also have 10 times 2, so equal to 20. So this reaction is balanced. So it's very important for every reaction to be balanced.